Hello, this is Pourhassan, and I'm going to present you the work related to high strain rate behavior of Alclad 2024 aluminum alloy using split Hopkinson tension bar. I'll start with the motivation, followed with the overview of the work, and also briefly talk about the experimental procedure, results, ongoing work, and finally the concluding remarks. The motivation of this work is to understand response of materials subjected to impact. It is known that the materials can demonstrate different responses when they're subjected to higher strain rates. So this type of information can be really useful in aeronautics and automotive industries, providing enough insight to optimize the crashworthiness of vehicles or can provide reliable input for crash simulations, replacing costly experiments. It can also be used in modern manufacturing processes where plastic flow behavior of materials could vary based on the loading rates. The material of this study is Alclad 2024 aluminum alloy. This material is mostly used in the fuselage and wing skin of small aircrafts, and also being used in the medium hull and narrow body aircraft such as Boeing 737. We studied the mechanical behavior of this material at various strain rates and temperatures. We also used thermography to measure the adiabatic temperature rise of the experiments at high strain rate. Here you can see the specimen geometry with the gauge lengths of 18. We used it for both static and dynamic experiments. And over here we designed the gripping system. You can see used it for experiments in Hopkinson bar. So the dynamic experiments were carried out using split Hopkinson tension bar. It's also known as Kolsky bar, includes two solid bars, incident and transmitted bars. The specimen is actually mounted in between them. So we impact incident bar using a striker, in this case is a tube, generating a stress wave which propagates throughout the bar, and when it comes to the interface between the bars and the specimen, part of it reflects and the other part of it transfers. So we have these strain gauges bounded on the bar, which records the amplitude changes in the signal, and then we analyze this signal. We record this signal. We analyze this signal using famous Hopkinson bar equations to obtain the stress strain behavior of the material. And you can see here the photo of our setup, a split Hopkinson bar setup. We have titanium grade 2 bars with a diameter of 16 millimeter and a Young modulus of 105 gigapascal. And we are able to reach a strain rate between 250 to 1200. We use PC oscilloscope from Pico to acquire the signals from Hopkinson bar, and we also use the Photon high-speed camera SA4 in order to record the whole event. We recorded at 86,400 frames per second at the aperture of 2.8 with a lens of 60 millimeter, with a focal length of 60 millimeter. And for the static test, which we performed it in the servo-hydraulic test machine, we used the point gray camera with a CMOS image sensor, and we record the event at 2 frames per second. We also did thermography on the specimens performed at higher strain rates and using FLIR thermal camera. And the recording frame was set to 2200 Hz at 80 by 64 pixels. We use the copper pulse shaper in our dynamic experiments in order to minimize the wave dispersion and achieve a nearly constant strain rate and facilitate the stress equilibrium. And here you can see the example of with and without pulse shaper. In the left you can see without, and in the left you can see the effect of using the pulse shaper, which significantly reduces the oscillations in the results. So high temperature, high strain rate experiments, we designed the heating chamber for Hopkinson bar. Basically, you can see in the image, it includes two resistive heating elements embedded into two copper plates, and it kind of covers the specimen and also the part of the grouping system. We also use four K-type thermocouples to measure the temperature on the copper plates, and also on another two to measure the gauge section of the specimen. The chamber is able to reach to the temperature of 250, and the reason for this limit was that above this limit we found that there is a negative effect on the Young modulus of the bars, which actually affects the stress wave propagation and obviously our results. So we weren't able to reach higher temperatures with this chamber. And in the right we have the environmental chamber, which we used for our static tests. We studied from room temperature and up to 350, and also the samples were kept around 10 minutes to have a more stabilized temperature inside the chamber. Here you can see the mechanical behavior of the 2024 aluminum alloy subjected to various strain rates. One thing you can see that is actually showing some negative strain rate sensitivity. We have the average tensile strength value of around 458 megapascal for static test, while the value is actually decreasing by increasing the strain rate. So this is something that actually we weren't expecting to see this, but in general aluminum alloys are known to be insensitive to strain rate, but seeing this negative strain rate sensitivity actually motivated us to perform some thermal imagery to understand what's going on in the material itself. And also the other thing is that failure strain value is actually increases by increasing the strain rate. You can see is around 31% in the strain rates, higher than 520. Here you can see the comparison between the strain values acquired using digital image correlation and also with the classic split Hopkinson bar analysis. And you can see that using Hopkinson bar analysis, the values are actually tend to be lower than the values recorded by the IC. And over in the right, we can see the in-plane strain distribution of the test sample impacted at a strain rate of around 500. And also we can see the progressive plastic deformation of the sample, which confirms that the rupture occurred within the first stress pulse. Using infrared thermography, we measure the thermal radiation emitted from the surface of test sample. The temperature distribution of the specimen is shown within the 200 microsecond interval in the left. And over in the right, we quantify the adiabatic temperature rise of the specimen impacted at strain rate of 500. You can see that that's only at 100 microsecond the temperature start to rise up by 3 degrees, which is the time the material reaches to stress equilibrium. And also we also pinpoint the temperatures, measure the temperatures, the average temperatures, and also the peak values recorded in the necking zone in the parentheses. And you can see from 15% strain rate of 50% and beyond, we are actually seeing not much change in the temperature. Also, having in mind the thermal diffusivity of aluminum alloy and very short duration of the impact, there's not much time for heat dissipation. So this causes a thermal softening, which could influence the plastic flow behavior of the material and possibly causing a negative strain rate sensitivity. Here you can see the strain map of the specimens enclosed within the environmental chamber, tested at static rate and exposed to various different temperatures. One thing we noticed was that for the temperatures of 300 and 350, there seems to deform in a limited region, and it seems that the temperature actually neutralizes the strain hardening mechanism. And this is actually something can be seen from the profile of stress strain curve, which I'm going to present you in the next slide. Over here is the material behavior as a function of temperature loaded at the static regime. As you can see, the material is not much affected up to temperature 100, but once it reaches to 200 Celsius, the strength significantly decreased to a value of roughly around 366 megapascal. And you can see here also that the profile of stress strain curve actually changes for the case of 300 and 350 centigrade, which appears to neutralize the strain hardening mechanism of the material subjected to such a elevated temperature. And similarly, the temperature effect for dynamic tests, which only performed at a strain rate of 500. You can see actually there is not much difference, almost no difference up to temperature of 50 Celsius. This could be because of some oscillations observed in this stress strain curve, but roughly speaking, there's not much change up to temperature of 100, but only around 5 to 16% drop in the strength value were observed for the case of 200 and 250 Celsius. And it's also noteworthy that in this experiment we weren't able to use the IC because the specimen was enclosed inside the chamber, and all the strain values, including the one in the room temperature, were derived from the Hopkinson bar analysis and not the IC. So we expand the work to two different materials, 2139 aluminum, and also additive manufactured specimens. In the case of aluminum, we performed the experiments at a strain rate of around 300 within the impact velocity of 7.5 meters per second. You can see the stress strain behavior inside. And in the case of additive manufactured titanium, the specimen is manufactured using the selective laser melting, which is a type of additive manufacturing technique, conducts layer by layer fabrication of the metallic powders. So we're hoping to have more in-depth study on this material, particularly studying the effects of residual stresses after manufacturing at various strain rates. So in conclusion, we studied the thermomechanical behavior of Alclad 2024 aluminum alloy at various strain rates and temperatures. We also designed a heating chamber for Hopkinson bar when we saw a notable temperature effect on the flow behavior of the material. Also, using infrared thermography, we record a notable adiabatic temperature rise, which appears to cause thermal softening in dynamic tests and resulting in the negative strain rate sensitivity of this material. Also, we expand experiments to two different materials, and we we obtained reproducible results with these materials. So thank you for your attention, and feel free to ask any question if you have.